Hey folks, today we're going to talk about vertical uniform circular motion. Just like all uniform circular motion, vertical uniform circular motion involves an object moving at a constant speed in a circle. But unlike the previous problems we've looked at, the motion occurs in a circle that lives in a vertical wall-like plane. So I'll give you an example of what this might look like. Unlike a car traveling in a horizontal circle, I have platy over here attached to a string. And to the best of my ability, I am swinging platy around at a constant speed, and platy is indeed moving in a vertical plane, engaging in uniform circular motion. So in the picture over here, I have this mint green string that is attached to the object, the mass over here, and the person in the picture is doing just what I was doing with platy. So mainly we want to understand how to appreciate the situation, how to understand the situation. And to help us with that, I have a specific task. We're going to try to find how strong the tension force is in the string at the three different locations, the top, the bottom, and the side. So let's start with free body diagrams. At each location, there is a gravitational force pulling the object down equal to mg. That force is equally strong regardless of where the object is located. There's also a tension force, and the tension force is always directed along the string direction. I'm going to label this FTS for the tension force at the side. I'm going to label this FTT for the tension force at the top of the circle, and I'll label this FTB for the tension force at the bottom of the circle. We're not assuming here that the tension force will be the same at all three locations. That's why I'm using different subscripts. So let's start our investigation by looking at the top of the circle. Newton's second law for circular motion tells us that the net force in the radial direction, that is the R direction, the center pointing direction, is equal to the mass of the object times its centripetal acceleration, the acceleration that points to the middle of the circle that represents how rapidly the object's turning. Now I see at the top of the circle both the tension force, FTT, and the gravitational force, mg, both point in the positive r direction. They both help each other out, pulling the object to the middle of the circle. And so they sum to mv squared over r, the value that the centripetal force must have. So in this case, the sum of F tension and gravity, that sum is what we call the centripetal force. Remember, the centripetal force is not an additional extra force. It is just the net force to the middle of the circle. All right, solving for the tension force at the top, we get mv squared over r minus mg. And it would be nice if we had some numerical values here. So let me give you some numerical values. Let's say the mass of the object is 2 kilograms. Let's say the radius of the circle is 4 meters, pretty big circle. And let's say the speed at which the object is moving is 8 meters per second. Okay, so let's figure out what these two terms are over here. The mass is 2 kilograms, so the weight, mg, is 20 newtons. If I plug in the mass value in the numerator here, that's 2. If I plug in the radius value, which is 4, I get 2 over 4, which is a half. And the speed squared is 8 meters per second squared is 64. So half of 64 gives me 32. newtons. And so overall, we have a 12 Newton tension force that's pulling the object to the middle of the circle. Okay, that's the tension force at the very top. It's 12 newtons. Now, we'll talk about that in just a moment by contrasting it with what's going on in the middle. So when the object is on the extreme right over here, what's happening now? Well, once again, we can apply Newton's second law for circular motion. My tablet is a little laggy. In fact, it's very laggy, so I'm sorry about the writing quality. When we look at the object now, at the middle, or the side, I've been calling this the side. Let me change that. We see that although there's a gravitational force acting on the object, the only force in the R direction, in the positive or negative R direction, is the tension force. So all by itself, the tension force on the side, FTS, has to equal mv squared over R. And we just calculated before, mv squared over R, if we plug in the numbers, is 32 newtons. And notice this is larger than the tension force at the top of the circle. So at the side of the circle, the way to understand this is at the side of the circle, the tension force is by itself responsible for providing the full centripetal pull. And that pull is 32 newtons. But at the top of the circle, gravity is helping out. See, gravity is kicking in this 20 Newton pull. So the tension force does not have to equal the full 32 newtons, but rather we could subtract the 20 Newton help that gravity is providing. And so the tension force is just the difference between those two things. It's 12 newtons. The string does not need to pull as hard at the top because gravity is helping to pull the object to the middle as well. Let's take a look at the bottom. At the bottom, we can apply Newton's second law for circular motion. And I see that, well, the tension force at the bottom, FTB, is pulling the object to the middle of the circle. But look, gravity is actually pulling in the opposite of the radial direction. Gravity is pulling in the negative R direction. It's pulling the object away from the middle of the circle. That's not helping to make the object turn in that circle at all. It's actually hurting the chances that that object moves in a circle. This time, when we solve for the tension force at the bottom, FTB, we get mv squared over R plus mg. Now I know what this equals. mv squared over R, we've calculated it a couple times now, is 32 newtons plus 20 newtons. And this equals 52 newtons. That's the biggest tension force we've seen so far. The reason the tension has to be so great when the object is at the bottom of the circle is because there is a 32 Newton net force that must be exerted to the middle of the circle for the object to turn in that circle. But gravity is exerting a 20 Newton force away from the center. That puts a great burden on the tension force to compensate for that by kicking in this huge center pulling force, nullifying the effects of gravity and supplying the additional 32 Newton force, which is needed. So the tension in the rope is always greatest at the bottom of the circle because the net force is always 32 newtons to the middle, but when gravity pulls away from the middle, tension force has to be bigger. And it's always the smallest tension at the top where gravity is helping out. Gravity is pulling to the middle, the tension force doesn't have to pull quite as hard. Now, let's say the string has a certain tension value beyond which it can't support the object and the string breaks. Because the tension force needs to be the biggest at the bottom of the circle, that is where the string is most likely to break. One moment, the motion sensors turn the lights off. So if you're swinging an object around in a circle and you go faster, 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 it's very unlikely to break up here. The rope simply doesn't have to pull so hard up there because gravity is helping. It's very likely to break near the bottom portion of the circle, where the tension force would need to be really big to make the object continue to turn. And when the rope breaks, because the rope is not capable of pulling that hard while staying intact, then the object will shoot off tangent to the circle. In this case, it would shoot off tangent to the circle and enter a parabolic free fall trajectory. And you can try this out. Take a heavy object on a kind of light string, go very slowly in a vertical circle, faster, faster, faster. Almost always it breaks at the bottom and flies off horizontally from the bottommost position. All right, now let's talk about something else. One more thing, in fact, which is the following. What minimum speed does the object need to move at in order to stay in the circle? Well, there's probably a minimum and a maximum speed. If I go too fast, then the tension force would have to be way too big. And the risk is that near the bottom of the circle, the string breaks if the object is moving too fast. But there is a minimum speed. This string is not going to break, so I can pretty much move it as fast as I want. But if I try to go too slowly, oh, it falls off. It doesn't complete the circle if it's moving too slowly. I need to make sure it's moving fast. Well, the risk is if it moves too slowly, then near the top of the circle, near the top, the object will fall out of the circle. Maybe that would look something like this. The object would fall out of the circle if it's moving below the minimum speed. If v is less than the minimum, and it's a laggy tablet. If v is less than the minimum speed needed to complete a circle, the object will not complete a circle and it will fall out. So let's try to find that minimum speed. We're thinking about the top of the circle here, because that's where the risk of falling is if you're moving too slowly. So remember, at the top, if you look right back up here, we said that the tension force at the top plus the weight of the object is equal to mv squared over r. Okay. So mg is a constant. That is not changing. If I move the object at a slower and slower speed, if I reduce the speed, well, the other side of the equation has to be reduced. But the gravitational force is not going to be reduced, so the tension must be reduced. The slower I move the object, the less the speed, the less the tension force needs to pull. But here's the thing. There's a minimum value that the tension force can have. The tension force can only pull to the middle of the circle. The tension force can only be in the positive r direction. So the smallest value the tension force can have is 0. In fact, when I'm moving at v min, minimizing the right-hand side of the equation, I have to minimize the left-hand side of the equation, and that means making the tension force as weak as it can be, which means no tension at all. In other words, when I'm moving at the minimum speed, when Platty is moving at the minimum speed in the circle, then at the very top of the circle, the tension force is actually zero momentarily. Gravity alone is providing the centripetal force, and the centripetal force doesn't need to be very strong because the object is moving slowly. So when the string goes slack, barely, that is when the object's moving at the minimum speed. Any slower, the object will free fall out of the circle entirely. Okay, so let's solve for that minimum speed. We have mg equaling mv min squared over r. And I see that the mass has nothing to do with it. So it doesn't matter if you're swinging around a brick or swinging around a fluffy bag of cotton swabs. The minimum speed needed to complete the circle, if we solve for it, is the square root of the gravitational field times the radius of the circle. All I did was multiply each side of this expression by r and then take the square root of each side. So how fast does something need to move in a circle in a vertical circle, to not fall off at the top to complete the trip? It only has to do with the gravitational field and the radius of the circle. In this case, we can find this value because the gravitational field is 10, the radius is 4, so we have the square root of 40, which is somewhere between 6 and 7. I'm going to say it's about 6.8 without taking out a calculator, about 6.8 meters per second. If the object moves faster than that, it's all good. The tension force just won't be zero anymore, and the tension force will pull down to ensure the object stays in the circle. At 6.8 meters per second, the string is not doing anything. Gravity alone is pulling down at the top, making it go in a circle. But if the object moves slower than 6.8 meters per second, it will plummet out of the circle. Now, let's think about this for a second. If the gravitational field were stronger, if the gravitational field went up, then the minimum speed would go up as well. Hopefully this is reasonable to you. Imagine that don't imagine. Look, I'm twirling Platty around. I know there is a minimum speed. If I go below that speed, the thing tumbles out of the circle. Well, if the gravitational field were stronger, if I were doing this on Jupiter, where the gravitational field is stronger than 10 newtons per kilogram, then there's an extra strong gravitational pull on Platty, and the risk is that, it's going to be that much more easy for Platty to fall out of the circle unless I make Platty move fast enough to not. So a stronger gravitational field means that thing had better be moving sufficiently fast to not fall out of the circle. Also, if the radius of the circle were made larger, if capital R were made larger, then the same thing would happen. The minimum speed would have to be adjusted upward to keep the object moving in a circle. See, if an object is moving around a circle like this, it's actually easier to keep the object moving in a circle of that sort. But if the radius is bigger, it's actually harder to avoid the object falling off. In fact, a really big radius circle, so I'm imagining like maybe a little roller coaster car here, around a tight, small radius turn, on a vertical loop, the roller coaster is not very likely to fall off. But the more gradual the loop is, the more likely it is for the roller coaster to fall off. In fact, if it were an infinite radius, then the object couldn't stay on that. It would fall down due to gravity alone. So making the gravitational field stronger makes it harder for the object to stay in the circle at the top, and it would have to move faster to avoid falling. And also making the circle bigger and more gradually turning makes it harder to avoid falling. And again, the object has to move faster to avoid falling down. Okay, there is a two-part homework, a assignment in the packet, and also some multiple choice questions on AP Classroom. Complete this over the break, before the break, if you're able, and we'll talk about this when we return on December 1st. Have a great one.